Okay, so line integrals. So it's different from what we did in chapter 15. In chapter 15, we integrated over regions in the XY plane for the first half of chapter 15, and then we started to look at integrating over three-dimensional objects, so solids. Here, we're just going to be integrating over a curve. Okay? So it's called a line integral, but it's generally not going to be a straight line. So it says line integrals were developed in the early 19th century to solve problems involving fluid flow, forces, electricity, magnetism. So instead of integrating over a general region, we integrate only over a particular curve. So a lot of these line integrals are used to find work done. And the easiest way for me to visualize it is like moving a particle over, a charged particle over, like through an electric field or something. So a lot of times I'll give you, okay, here's what the vector field looks like, and here's the path you're moving the object along. And so how much work is done in that scenario. Okay, so it says we start with a smooth plane curve C. Remember, smooth just means it's differentiable and the derivative is never zero, given by parametric equations or by a vector equation. Okay, and then that just reminds us of the definition of smooth. Okay, so it says suppose that the vector equation, so this is how we get C. Okay, so there's the vector equation of the curve. And we assume that curve is smooth on some interval AB. This AB, this is an interval for t. So that's like your time. If we divide that time interval into small parts of equal width and let x and y be the corresponding points on the curve that divide the curve into these sub-arcs with different arc lengths. So before I go on, let's just talk about that. So even though the times are equally spaced, so say I take a measurement every second, just because the times are equally spaced doesn't mean I'm breaking the curve up into equal pieces, because sometimes the particle might be moving really fast and sometimes it might be moving really slow. So just because time is equally spaced doesn't mean my endpoints are equally spaced. So maybe I'd get a really long one, maybe the object is moving really fast, and then it kind of moves slow. So maybe it does something like that. And then it divides our curve into these separate little arcs. And what we want to do is approximate the arc length of each segment. I'm just going to focus on this one right here. So I want to approximate that length, and the easiest way to do it is to just approximate it with a line segment. Now, that's not a great approximation, but remember the process we always do is we start out with one partition and then we keep like cutting it into smaller and smaller pieces. And the smaller my piece gets, the better a line segment does approximating it. But I wanted to kind of use a big one so we can see what's going on here. So this is gonna, that length that I've drawn right there, that's going to approximate the arc length for that piece. Okay, well, how am I going to figure out that length? Well, I can make a right triangle out of that. And if I did that, what could I call this side? Well, the delta S is the hypotenuse. Think of delta something. What? Delta X, right? This one we could call delta X, and this one we could call delta Y, and then we'll use the Pythagorean theorem. And so we would get the delta x squared plus delta y squared equals delta s squared. So delta s is approximately the square, and I should say this is approximately delta s, right? I'm using the hypotenuse to approximate that. So delta s is approximately the square root of delta x squared plus delta y squared. And then how we get from here to here is basically under the square root, we multiply and divide by delta t squared. And so I'm going to distribute this delta t squared in the denominator to each term. And so I would get delta x over delta t squared plus delta y over delta t squared, but then leave the one in the numerator. So this one got distributed in, but leave the one in the numerator, and the square root of delta t squared is just delta t. And then we know when we take the limit as the number of partitions goes to infinity, the deltas turn into differentials, right? So the total length of the curve is the integral going from time 1 to time 2, or a to b, of square root of dx dt squared plus dy dt squared times dt. And you should have seen this in your Calc 2 class, but again, it might have been a while since you've had Calc 2. Okay, so here I said I took a break to talk about how to get the delta S, but then to evaluate what we are calling the line integral, it says we choose any point in the subarc. You could choose either of the endpoints or the midpoint. You could really pick any point you want, and then evaluate that function that we're given. So we're going to be given a function of 2 variables. We want to evaluate it at either the endpoints or the midpoint or whatever, and then multiply by the length. So what that's going to give us, the f is going to be like our height, and then the delta s is going to be our length. So we'd have height times a length, or base times height, if you want to think of it that way. So if you do base times height, what the final quantity is going to give us is an area. And this is how I personally like to visualize it. It's like this is the path, and you're building a wall on that path. And so what the line integral is going to calculate is what's like the surface area of one side of that wall, basically. And so this was the sum. We did the height and the length for each little subarc. Take the limit, you add them all together, and the delta S turns into ds. And so this, what I just did was showed you that the ds, this is what calculates arc length. So when we go to do the entire line integral, so we're integrating over a curve. Our function, f of x, y, with respect to arc length, but the arc length we have to replace with this. Now, a really important thing, when I go from here to here, this says arc length and a curve, and this says time. Time goes from A to B. We can only have as many variables as we have integrals, right? So if we just have one integral, we can only have one variable. So one integral means one variable. But even what comes before one integral means one variable is one, this capital D means dimension, so one-dimensional object. So if you have something that's just one-dimensional, then you can only have one integral. So this part's a little bit tricky to think of at first. because you think, well, here, when I look at this curve, that's in two-dimensional space. But when you think about, like, I can make this wire like curvy, right? And it looks, yeah, it's in, well, right now I have it in three-dimensional space, right? But when you think about that curve, 3 dimensions means length, width, and height. Does this curve have all 3 of those? It only has a length, right? It's curved around, but it doesn't have a, I mean, this wire has a little bit of a width, but when you think of just like super thin wire that doesn't have a width and it doesn't have a height. So curves are one-dimensional, even if they live in 3-dimensional space or 2-dimensional space. Curves are one-dimensional. The only thing they have is a length. Okay? And so if we're dealing with a curve, everything better be in terms of just one variable, which is, I tend to use t as my parameter. Okay, so then whenever we have an x and a y in the integral, we just have to replace it with its parametric equations. So let's look at an example. Okay, and so I have, so we're integrating over a curve, so that means one-dimensional, which means at the end, I can have an integral only in terms of one variable. And then y over x ds. I think what I'm going to worry about first is the ds. So I know that my ds is the square root of dx dt squared plus dy dt squared. And then, well, you may have a dz dt squared, but I see here my curve only has an x and a y. Okay. So this right here in the xy plane, this is my curve, see? And then I'm just showing you, so what's our f of xy? Okay, if I look here, it says integrate over a curve some function f of xy with respect to our plane. So is what? Y over x, right? It's the integrand. So every point on the curve gets plugged into the function, and then whatever number I get out, that gives the height of the wall, right? So this is the wall I'm going to build on that path. And when I'm done evaluating the line integral, it should give me the area, the surface area of one side of that wall. And then a dt at the end. So for this problem, what's dx dt? 4t to the third. And what's dy dt? 3t to the second. Okay, so our ds is the square root of, so when I square that, I get 16t to the sixth. Plus, and when I square that, I get 9t to the fourth. I'm going to simplify that a little bit before I go on. What's the only thing we can really do with that? Yep, take out a t to the fourth, and then we'd be left with 16t squared plus 9. And then the square root of t to the fourth is t squared. Okay, so again, one integral, curve is one-dimensional, one integral, one variable, it's got to be t. So the limits on my integral are the limits for t. And so what are the limits on my integral then? 1/2 to 1. What am I going to put in place of y? Right, so I'll have t cubed for y, and then for x, t to the fourth. Yep, so that will simplify to be 1 over t, and then my ds gets replaced by this. t squared times the square root of 16t squared plus 9 dt. So in the top, we have t to the 5th, and in the denominator, we have t to the 4th, so we just are left with a t. And how are we going to integrate that? U sub. So u equals 16t squared plus 9. du equals 32t dt. And we just have t dt left, so I'm going to multiply both sides by 1 over 32. And then what's our new top limit? 25. And the new bottom? 13, right? Because 1/2 squared is 1/4 times 16 is 4, plus 9 is 13. Okay, I'm going to pull the 1 over 32 all the way out in front. And this goes from 13 to 25, and then the t dt was getting replaced by 1 over 32 du, and then I have u left under the square root, u to the 1/2. So the new power of u is 3/2, which means we want a 2/3 out in front. And this is going from 13 to 25. 2 goes into 32 16 times. So I have 1 over 48. And then when I plug in 25, I get 25 root 25 minus 13 root 13. But root 25 is 5. And if you have 5 quarters, that's $1.25. And then the 13 root 13, that doesn't simplify. Here, it is possible to get negative answers. That would be like if you built your wall under the XY plane. We didn't do that. Our wall is always above the XY plane. But if you do go below, that kind of means like you're digging stuff out instead of building. So it is possible to get a negative if most of your function is below, or most of the wall is below the XY plane. Okay, so this time they don't give us, the last one they gave us X, they gave us Y, they gave us our limits for T. Here they don't do that, which means we have to come up with it ourselves. But they give us a description, and C is the line segment, so in 2-dimensional space joining 1, 2 to 4, 7. So we have to come up with an equation, or come up with equations, parametric equations for C. I'm going to worry about the fact that it's a segment in a minute. What I'm going to focus on right now is it's part of a line. And so if we want the equation of a line, what do we need? Point. That's for a plane. Yes, slope, but direction. We just call it direction. So our point, we're going to use the starting point is 1, 2. How do we figure out the direction of the vector? Ending minus starting, right? So 4 minus 1 is 3, and 7 minus 2 is 5. Okay, so then our x is 1 plus 3t. Our y is 2 plus 5t. And now since it's a segment, That if I just left it like that, that gives me a line that goes forever. I want a segment. T goes from 0 to 1. Always when you do it this way, T goes from 0 to 1. You can check. When you plug in T equals 0, you get 1, 2. When you plug in T equals 1, you get 1 plus 3, which is 4, and 2 plus 5, which is 7. Okay, so now we're at the point where we started out on the last one. We have the X, we have Y, we have limits for T. So the first thing I want to do is find DS, but before I do that, I just want to mention that there are some problems on the group work that instead of DS, they might just have DX or DY. So if they just have DX or DY, then you don't need to find DS. You just would need to find DX or DY. Okay, so what is, but we do have DS. And so remember, DS is the square root of dx dt squared plus dy dt squared dt. So in our problem, what's dx dt? 3. And dy dt is 5. So ds is the square root of 9 plus 25 dt, or the square root of 34 dt. So now that I know what I'm replacing ds with, and I need to get, again, one integral, one variable, everything has to be in terms of t. And we know our limits for t are 0 and 1. What am I going to put in place of y? Yep, 2 plus 5t. And then e to the, what am I going to put in place of x? 1 plus 3t. And then the ds is square root of 34 dt. So we can bring the square root of 34 all the way out in front. And if you want, you can distribute the e through, I'm just going to leave it like this. What method are we for sure going to have to use to integrate? Well, parts, right? Which is the product rule for integration. And so here, like I said, you can multiply out, but you can just use the whole thing as your u, the 2 plus 5t, and we can do the table. Because if this is my u, I will eventually get to 0 when I take derivatives. So my u is 2 plus 5t, and then when I take the derivative of that, I get what? 5, and then when I take the derivative of 5, I get 0. Okay, so here's the trickier part. So e to the 1 plus 3t. So when I take the antiderivative, I get e to the 1 plus 3t, but what else do I get? 1/3 or over 3. And so if I take the antiderivative again, I just get another factor of 1/3, so 1/9. And then we do diagonal products, alternating signs. So I'm going to bring that square root of 34 all the way out. Okay, so I'd have 2 plus 5t. Actually, the first thing I'm going to do is, so I just don't have to write it twice. They both have an e to the 1 plus 3t, so I'm just going to go ahead and factor that out. So then if that's gone, I have 1/3 times 2 plus 5t minus 5/9. And this is going from 0 to 1. Okay, so when I plug in 1, I get e to the 4th. Okay, 2 plus 5 is 7, so I get 7/3 minus 5/9 minus what I get when I plug in 0. So that would just be e to the 1, or just e. And then 1/3 times 2, so 2/3 minus 5/9. Okay, common denominator is 9. So 21 minus 5, 16. So 16/9 e to the 4th minus 6 minus 5, 1/9 e. If you wanted, you could factor out a 1/9. You could also factor out an e if you wanted to factor out everything. I'm just going to leave it with this. Okay, on Tuesday, oh, nope, let's do one more example, and then we'll start with the vector fields part of it on Tuesday. So we'll do one more where we just have a scalar function. It's the same as what we've been doing, it's just we're in, our function is a function of 3 variables. Okay, so line integrals in space, 3-dimensional space, very similar. It's just our ds has the extra dz dt squared. But other than that, it's the same. So it says, note that we can express this more compactly using vector notation as follows. And the reason is, remember the C, the parametric equations for C, we have x equals x of t, y equals y of t, z equals z of t, or we can put it in vector notation, right? R equals x of t, y of t, z of t. And then what would R prime be? What's the first component? Yep, dx dt. And then dy dt and dz dt. And if I take the magnitude of R prime, well, the magnitude of a vector is the square root of the sum of the squares of its components. So it'd be the square root of dx dt squared plus dy dt squared plus dz dt squared. So this whole thing just gets replaced by the magnitude of R prime. Just so you don't have to write that whole formula. I usually do just write the whole formula, but you can write it this way as well. For the special case that f of xyz equals 1, we just get the length of the curve. Because remember, in general, I say C is the path we're building on, and the function value gives the height of the wall. So each little piece of the curve would be length times height. But if your integrand is 1, then your height is always 1. So you'd have length times 1, which is just going to give you length. Okay. All right, so let's do problem 12. And again, we're at a problem where they give us x, y, and z in our limits for t. So what's dx dt? 1. What's dy dt? 2t. And dz dt? 3t squared. So our ds, I'm just using this up here, is the square root of, so dx dt squared would just be 1, dy dt squared would be 4t squared, and dz dt squared would be 9t to the 4th dt. And there's nothing we can do to simplify that. There's nothing they have in common. I can't factor that. So I'm just going to leave it like that for now. one integral means one variable. I have to get everything in terms of t. And they tell me the limits are 0 and 1. And what am I going to put in place of x? T. I'd have 2t plus 9. And what am I going to put in place of z? T cubed. And then the ds gets replaced by this. Okay, so this looks horrible, but what should we always at least try? Right, let's just try a u substitution. So what would we let, if we did, what would we let u be? Yeah, everything under the radical. And then du would be 8t plus 36t cubed. Can I multiply both sides by a constant to make it look like that? Yeah, if I multiply both sides by 1/4. So it's going to work. But what is our new top limit then? 14. And what's the new bottom? 1. Okay, so this part is being replaced by the 1/4 du. Oh, I wrote 0 and 1, but it's not. Right? We have new limits, 1 to 14. So 1/4 du, and then what's left is u under the radical, so u to the 1/2. So bring the 1/4 out in front. The new power is 3/2, so 2/3 goes in front. I'm going from 1 to 14. 2 goes into 4 2 times. So I get 1/6, and then 14 root 14 minus 1 root 1.